This is Unit 2, which deals with the first law of thermodynamics. In this chapter, we're going to start looking at some of thermodynamics' most fundamental principles. The most fundamental basis for the study of thermodynamics is the theory of the conservation of energy. It tells us that energy can neither be created nor destroyed, but it can only be transferred or transformed from one form to the other. How the conservation of energy principle can be used is what we're going to be looking at in the first law of thermodynamics to see how this information is useful to us in learning, predicting, and assessing what takes place in physical and chemical processes. Energy is necessary for everything that we do in life. And practical thermodynamics actually allows us to be able to quantify reactions that make life processes and other processes that we use for our daily life possible. For example, when we think about when we drive our cars, we get mechanical work from the burning of fuel in our gas tank. When we think about our respiration and our heart beating and all of our life activities, we get the energy from the food that we consume. So, thermodynamics underlies as a fundamental principle everything in our life. It helps us to be able to quantitatively understand what's going on and to help us to be able to make predictions about what we expect to happen in a chemical reaction and reaction system. These are a couple of slides that show you just some very basic examples of thermodynamics at work. When you think about your refrigeration and air conditioning systems, there is an exchange of energy from the internal environment of the refrigerator or air conditioner unit and the surrounding environment. Another example is our gas turbine engines. What we see in our jet planes, in our power plants, there are engines in our car, and they all operate based on the production of mechanical work from a heat source. Our power plants are a prime example of the conversion of energy from one form to the other. We get electricity that allows us to be able to do work in our everyday lives in many, many different ways from heat, which is produced from burning fuel or nuclear reaction or many other ways that we can get heat. But the basics are the conversion of energy from one form to the other to allow us to be able to do some quick examples of the things or things that thermodynamics has a fundamental input into when we make considerations on these subjects. Of course, we know that thermodynamics is essential to our bodily functions. We just discussed it. One thing that we are going to do in this course, as we discussed earlier on in the theme of sustainability, is to think about how the thermodynamics of energy production allows us to be able to learn more about alternative energy sources. So some of those alternative energy sources, we already spoke about the carbon dioxide problem, the CO2 emissions being a great contributor to global warming in our environment. And so what we're going to do as a side project after we are done with this unit is to look at a couple of these different alternative energy sources, alternative or renewable energy sources, and see what are the pros and the cons, how much energy input, how much energy output, what is the cost associated with it, what are the environmental implications, what are the political implications. We're going to look at some of these examples in a separate project at the end of this unit. But some of the most popular forms of alternative or renewable energy are solar, geothermal. We think about getting energy from biomass, from nuclear, from the wind, hydrothermal, and from fuel cells. So we'll talk about, we'll talk about these a lot more as we go on. So the study of thermodynamics is broken down into two basic branches. We know that we've been saying that the study of thermodynamics is relating to understanding the transformations of energy, basically heat into work and vice versa. So classical thermodynamics deals with what we see in the bulk. We already talked about the difference between macroscopic and microscopic. So classical thermodynamics deals with what we can measure in our everyday surroundings in the bulk setting. We can take a temperature, we can measure a volume, we can measure the pressure. On the other hand, statistical thermodynamics, and actually more fundamentally quantum mechanics, quantum chemistry, quantum mechanics is the branch that accounts for how molecules, ions, the smaller particles on the very small scale actually behave, and how that behavior translates in to what we observe in our bulk setting. So basically what happens at the level of the molecule, the ion, or the atom, and how that translates into what we observe on the bulk scale. So when we think about classical thermodynamics or chemical thermodynamics, we have three different areas that we consider. One is electrochemistry, one is thermochemistry, and the other one is bioenergetics. Thermochemistry has to do with the transformations of heat, the study of heat transfer during a chemical reaction. Electrochemistry has to do with the study of the thermodynamics of the flow of electrons in electrochemical processes. And bioenergetics has to deal with energy transfer in a living system. So when we actually undertake this study of thermal, we think about what the object under study is. When we're talking about quantifying what's taking place in a thermodynamic system, we have to know that the universe is divided into two parts: the system and its surroundings. The system is the part of the world that we're actually studying. The surroundings basically is everything else. So looking at a graphical representation of that, what I just said, the system, the object under study, and the surroundings is everything else. So basically the universe is composed of the system plus the surroundings. Now there are going to be some cases on the practical scale. When we're in the lab, for example, we're going to have to identify, sometimes we have to limit the amount of surroundings that we consider to be a part of our little universe for our reaction. So those considerations we'll see are going to become more important as we go into lab, as we go throughout the semester. But there are three different types of system. An open system is able to exchange matter and energy with its surroundings. A closed system is able to exchange energy but not matter. So if we think about an open system, that would be just like a beaker of a liquid sitting on our bench top in our lab. A closed system would be like an Erlenmeyer flask with a stopper in it, or something type of container that's closed that has a sample in it that you can't put anything into. And an isolated system has the inability to exchange neither, it cannot exchange either matter or energy. Think about your thermos. Your fully isolated system that is unable to exchange energy with the surroundings or matter. The way that we describe the total energy in a system is through the state function, the state variable, U, which is the internal energy. The internal energy is the sum of all of the total potential and kinetic energy contributions to the system. We can't explicitly measure the internal energy of the universe because it's impossible. But what we can do is measure the change in internal energy when we go from initial state to a final state in a system. So what we actually measure on the practical in the practical world is the change in internal energy, which is equal to delta U. And that function is the final internal energy of the system that we're observing minus its initial internal energy. Now, internal energy is a state function. So we remember what that means, right? If we go from an initial state to a final state, it does not matter how we get there. We can go straight there. We can take a detour all around the world if we want to get there. But as long as we end up going from the initial state to the final state, it does not matter how you get there. And that's the same way if we were to think about going from Alcorn here to Port Gibson. Let's say we're going from campus to Sonic. It does not matter whether you go down the back road, whether you take 61, whether you take the natural straits. All that matters is that you get from campus to Sonic. So that is the definition of the state function. So in terms of energy, our energy unit that we're going to be using is the joule. Okay, the unit of the joule is broken down into its SI basic fundamental units. A kilogram, meter square per second square is the same thing as a joule. Other units for energy measurement are the calorie, and there are conversion factors to get us from joules to calories, and the electron volt, or EV.